Dear students, in this video we are going to discuss about Dining Philosopher's problem, that is another example for classic problems of synchronization. In Dining Philosopher's problem, there are n number of philosophers sitting round the table and there will be a bowl of rice in the center of the table and there are two chopsticks on the either side of the philosopher. The philosopher may be either in the thinking state or hungry state or eating state. Suppose if the philosopher is in thinking state, he don't make use of the chopsticks and the rice. When he is hungry, he will be entering into eating state. So when he want to eat, then he has to pick the chopstick in the left and right hand side of the philosopher. Then only he can take the rice from the bowl and then can enter into the eating state. Suppose if the philosopher is not able to pick any one of the chopsticks, then he cannot enter into eating state. So therefore, for the philosopher to enter into the eating state, he should pick both the chopsticks, that is on the left hand side and on the right hand side of the philosophers. So in this example, there are 5 philosophers sitting round the table and there are 5 chopsticks available on the table. So on each philosopher's side, there will be one left chopstick and there will be one right chopstick. A philosopher needs both the left and right chopstick to enter into the eating state. Once he completes eating, he releases both the left and right chopsticks. He can take the rice from the center of the table only when both the chopsticks are available. Initially, the chopsticks are initialized to 1. That means the chopsticks are available. Then the philosopher pick the first left chopstick, then he will pick the right chopstick, then he takes the rice from the bowl and then he will be in eating state. So once he complete the eating, then he releases the left chopstick and then right chopstick. The structure of the Dining Philosopher's problem algorithm is as given in the slide. Initially, the philosopher tried to take the left chopstick, then he tried to take the right chopstick. So he called the weight function on left chopstick. Then he calls the weight function on the right chopstick. Suppose if the chopstick value is 1, that means the weight function will not block the philosopher. If the chopstick is not available, then the corresponding value of the chopstick will be 0. Then this weight function on the chopstick will block the philosopher until the chopstick value is turned to 1. In that way, the philosopher who calls the weight function will either take the chopstick or will enter into a blocking state based on the availability of the chopstick value. Now let us assume that initially all the chopsticks are initially available. So they are initialized to 1. So the first philosopher who is trying to take the left chopstick, he will be successful in taking the chopstick. So that is ith philosopher is successful in taking the chopstick I. Then he tried to take the right chopstick. The right chopstick is I plus 1 mod 5. So if I is the philosopher, the left chopstick is I and the right chopstick is I plus 1 mod 5. So in this way, if the right chopstick is available, then the philosopher will not be blocked here. He will take the right chopstick also successfully, then he will enter into the eating state. Once the philosopher completes his eating, then he releases the left chopstick by calling the signal function. Calling the signal function on the chopstick value increments the chopstick value. That means previously the chopstick is turned to 0, so it is incremented, so 0 becomes 1. Similarly, right chopstick also he will increment by calling the signal function. So in that way, the chopsticks again will be turned to 1 after completing the eating. Then the philosopher will enter into thinking state. In this way, the philosopher will pick the left and right chopsticks, then go to eating state, then releases the left and right chopsticks for the availability to another philosopher. So now let us take up one example. So assume that I is equal to 2. So philosopher will try to call the weight function on the chopstick of I. That is, the chopstick of I means the left chopstick for the philosopher number 2. So if initially all the chopsticks are 1, so therefore the calling the weight function on chopstick will not block the philosopher. So he will get the chopstick successfully. Then the 1 will be turned to 0 now. Then philosopher will call the next chopstick, that is I plus 1 mod 5. So I'm substituting the I plus 1 is 2 plus 1. 2 plus 1 is equal to 3 mod 5. So 3 mod 5 is equal to 3. So therefore the philosopher will take the right chopstick successfully because the right chopstick is also available. Initial value of the chopstick is 1. No other philosopher is in eating state. Therefore this chopstick is also available for the philosopher too. So therefore after applying the weight function call on the chopstick number 3, it will turn the chopstick value to 3, and then the philosopher is successful in both left and right chopsticks. Then he will enter into eating state, and after completing the eating process, then the philosopher releases the left and right chopsticks by calling the function signal of chopstick I, signal of chopstick I plus mod 5. I plus 1 mod 5. So in that way again the C2 and C3 values will be turned to 1 after completing the eating. For example, if I is equal to 4, what is the left chopstick and right chopstick? So I is equal to 4 means the left chopstick is 4 and the right chopstick will become I plus 1 mod 5. The 4 plus 1 mod 5 will give you 0. So therefore the left chopstick value will be 4 for the philosopher number I is equal to 4, and the right chopstick will be 0 for the philosopher number 4. So in that way the mod function will be used for generating the values from 0 to 4 in circular fashion. So what are the problems with this dining philosopher problem? For example, if all the philosophers pick the left chopstick first, then this leads to a deadlock state. For example, every philosopher is taking their left chopsticks. So P1 selects left chopstick, P2 chooses C2, P3 chooses C3, P4 chooses C4, P0 chooses C0. So every philosopher is successful in getting his left chopstick. Then every philosopher try to get the second chopstick, that is the right chopstick. But already this right chopstick is already taken by the next adjacent philosopher. So therefore every philosopher will be in the waiting state until the chopstick is released by the adjacent philosopher. Likewise, every philosopher will be waiting for the chopstick to be released by the adjacent philosopher. Without knowing each other, all the philosophers will enter into a deadlock state waiting for the adjacent philosopher to release the chopstick. But this process will never terminate because all the philosophers will enter into a deadlock state. So this is the problem with the dining philosopher's problem. How to resolve this deadlock in the dining philosopher's problem? There are 3 solutions are provided to handle this deadlock situation in the dining philosopher's problem. The one situation is allow at most 4 philosophers to be sitting simultaneously at the table. That means we provide 5 chopsticks and we allow only 4 dining philosophers to sit on the table in order to take the food from the table. Therefore, one philosopher will be successful in taking the both left and right chopsticks. Then the philosopher will enter into a eating state. After completing the eating process, the philosopher releases the chopsticks. In that way, these chopsticks will be available to the other philosophers. In that way, the philosophers will not be blocked. Hence, deadlock is avoided. The second alternative solution is allow the philosophers to pick the chopsticks only when both the chopsticks are available. That means when the philosopher takes one chopstick and see that there is no chopstick in the other side, then the philosopher should release that chopstick also, because he is permitted to take both the chopsticks only when they are available. The third alternative solution is allow odd number philosophers to pick the left chopstick and allow the and then right chopstick. Allow the even numbered philosophers to pick the right chopstick first and then the left chopstick next. In that way, allowing the philosophers to take the chopsticks in the alternative ways, this makes one philosopher definitely take both the chopsticks successfully. In that way, he will enter into eating state. After completing, he releases 2 chopsticks. Those 2 chopsticks will be available to the adjacent philosophers. In that way, the deadlock will never happen if this solution is adapted. So in that way, we can handle the deadlock situation in Dining Philosopher's problem by allowing these methods of taking the chopsticks. What are the problems with the semaphores? The incorrect use of the wait and signal functions makes the system to enter into a deadlock state. That is, calling the signal function before wait function makes more than one process to enter into the critical section. That is not permitted. So this is the disadvantage with the usage of the signal function before the wait function call. The next problem with the incorrect use of the semaphore is when we miss signal function. So instead of signal function, here we are calling the wait function itself. That is, calling the wait function after the wait function. This makes one process to enter into a deadlock state. Omitting either wait function call or signal function call makes the system to enter into a deadlock and starvation possible. These are the problems with incorrect use of the semaphore operations. Thank you for watching this video.